In this lesson, we'll learn the probability distributions and some basic concepts about the probability distribution. The PDF, CDF, and the expected values, these are the terms that are frequently used in statistical inference. Later on, we will have to use this distribution to quantify the probability of events happening, because when we try to make a statement about the population parameter, generally we try to use contradiction, proof by contradiction, by calculating certain probabilities. And that probability might contradict what is in the statement. So we will first need to get familiar with these terms and also how to use them. The random variable includes the discrete random variable and the continuous random variable. Discrete refers to those variables that only have a few possible values. More accurately, discrete variable refers to those variables whose values can be counted one by one. Even if there are infinite many of them, as long as they can be counted, that's discrete random variable. On the other hand, a continuous variable refers to the variables whose possible values are including an entire interval. For example, the time until completion of the first assignment. The time it took to complete the first assignment. So that's an entire interval that different persons would have different amount of time used to work on the homework assignment. So that entire interval could be possible values. For any single number, in a continuous variable case, the probability of a single number is 0. This is the principle. In fact, the reality in real life, we do not have measurement skills as fine as possible. For example, in terms of time, we mostly can be able to get measurement accurate up to second because we do not have the smaller unit in everyday life when you work on the homework. So due to limited precision or accuracy in the measurement, what you see quite often is not really infinite amount in the entire interval. Instead, you still might be thinking of that as a discrete variable, but unfortunately, discrete variables are a lot harder to study because most of those properties involve summation, and the summation is not as easy as the discrete variable, which would rely on integral. So statisticians mostly would try to use a continuous model to approximate the real-world situation. And in fact, these continuous variables approximate the real-world situation better and make it much easier to work with. Probability distributions for the continuous variable are defined as a function, the PDF, okay? This probability distribution function is a PDF. PDF simply is a function such that the probability of the variable between two numbers is given by the area and the curve. So basically, imagine if you have the fx, this f has to be greater or equal to 0, fx greater or equal to 0, and then there is a probability that this probability is given under the curve A and B and above the AB. So this part gives the probability for x between A and B. The curve here is the fx, and that's the probability density function. Quite often, what we want is the probability to the right of the curve, for example, to the right of some point, like this value, This is a given value, and we want the probability of greater than x0. And this one is the probability of x between A and B. And sometimes we also care about the probability to the left of a value. So this is the probability density function for any of the A and B. As long as you have the density function, you will be able to get the probability computed. This F, in order for that to be a legitimate PDF, it has to satisfy that one is non-negative, because if you have a negative part, and then the interval on that negative part, when you integrate it, it will become negative, but we can never have a probability being negative. So this F has to be always greater or equal to 0. The next one is since the interval integration on the interval give us probability. So if we consider the lower bound to be negative infinity, upper bound to be positive infinity, then the integration will give us the total probability for all the scenarios, all possibilities. Therefore, this should be 1. So you integrate the density function from the smallest to the largest possible value, we'll get 1. Note that here, the notation, we put the negative infinity and positive infinity in the integration, but in the real life, the variable positive values may not need to go from negative infinity to positive infinity. For example, quite often we use a variable, normal variable, to a normal standard normal distribution to measure to describe some kind of noise, and that variable mostly the values are all between -4 to +4. So if we consider the integration here, we still can write the negative infinity to positive infinity. That's because the rest of that beyond the range from -4 to +4, the rest of that has probability 0. So it's still fine. Okay, this is the PDF. So summary, PDF is the function such that when you consider the probability of the variable in an interval, then this probability is given by the area under the PDF curve above the horizontal axis. Here A and B are the two numbers. A could be negative infinity and B could also be positive infinity. So if A is negative infinity, we're looking at the probability of x less equal to a number. On the other hand, if B is positive infinity, then we are looking at x greater or equal to a number. Okay. Where is the PDF really from? We know about the histogram. Basically, PDF was trying to approximate, giving a smooth approximation when we consider to use the histogram. So like in the picture here, that we have a panel A, that's a histogram with a very big intervals, and B would be having more of the intervals, and C is when we have the curve become smooth. So essentially, when you have a small amount of data, you might just plot the histogram with A, and on the other hand, when you have more and more data, you could refine the interval in the histogram, so the intervals will become smaller. As you keep going, consider all possible values of that variable, and infinite many of them would allow you to get the interval being smaller and smaller, so that the histogram becomes the smooth curve. This is for the continuous variable. In the discrete variable, on the other hand, we might call the probability density function as a PMF, probability mass function. That the reason that we do that, this PMF, probability mass. we assign a probability mass to each of the possible value. For example, we have x1, x2, and x3, and the probability for x1 is given by p with the x1 there. Subscript x represent this is for variable x, and little x1 here represent this is the value for this variable x. So the x1 is a possible value, then we have a probability for that, then we put a bar here. Similarly, if x2 is a possible value, we put a bar here for x2. And the height of the bar is the probability of x2, and so on. So this is the case of a discrete variable. We only have these bars. Each bar height represents the probability. This is the discrete case. Discrete PMF probability mass function, because each possible value was assigned a probability mass to that. In the continuous case, when we consider the probability, we were given the continuous curve. That's because all these bars are eventually going to be connected, since the entire interval is possible. Our entire intervals are possible values of the variable. And in the discrete case, if we want to consider the probability, for example, for interval A, this interval contains the possible values like x2, x3, then that probability simply would sum up those bars inside of this A. On the other hand, in the continuous case, the same A here, what we are going to cover is the entire range, and rather than having single bars that we can count or add together. But for this interval A in the continuous case, when we try to add up, imagine if you try to have these little bars, infinite many of the bars with very small width. Eventually, when we add those up, what we get is the integration under the curve. So this is the approximation. In the discrete case, you do the summation. In the continuous case, we integrate. The two essentially are actually giving the same concept. Here's an example. For this example, we are looking at the current in a circuit. And this is measured as a continuous variable with this density. This density means the PDF, okay? So density just means the PDF, probability density function. With this density, find the value of C. This kind of question basically is testing us the knowledge that for a density function, if you consider the entire interval, then the probability of that entire interval should be 1. So we use that knowledge to find the value of C. So for this case, we'll try to integrate the f from 3 to 5, and then we make it equal to 1 to solve for the C. So in particular, for this one, we will have a integral from 3 to 5, and then 0.075 x plus C, and integrate with x. The first term will give us 0.075 and times the half of the x squared. Second one is the cx, and these are going to be evaluated from 3 to 5, and that will be supposed to be equal to 1. So on the right hand side here, if we try to evaluate that, what we get is 0.075 over 2, and they have the 5 squared minus 3 squared, and then the next term would be simply c times the 5 minus 3. And this is supposed to equal to 1. When we solve for that again, 25 minus 9, that's the 4. 4 squared, 16, 16, 8. So 8 times 0.075, and then plus the 2c equals 1. So the 2c is equals 1 minus 0.6, 0.06, 0.6, okay. So this 8 times 0.075, well, that's about 0.6. So therefore, we get the C equals 0.2. So that gives us the answer of C. So C was obtained simply by integrating the density function on the entire range of possible values. And that should be 1 from there to solve for the unknown C. The part B here, calculate the probability of x that's equal to 4. And this one, when we calculate that, we will integrate from 3 to 4, and we'll put in the density function 0.075 x plus c and dx. And this will give us the probability. But c now, we can put in the 0.2. When we do the computation, we will get the 0.075 times the 4 square minus the 3 square, and then plus 0.2 times 1. 0.2 times 1. So 0.075 times 7, and then plus the 0.2. So that will be the answer. Okay. The next one, calculate the probability between 3.5 and 4.5. This would be similar. You see, previous one, even though we only have less equal to 4, but the lower bound we still put 3. That's because 3 is the lowest possible value for fx to be non-zero. Because the rest of that fx is 0, so we do not put a negative infinity. The next one, we would integrate from 3.5 to 4.5, and then you also put in the density function here, and then integrate it. So what we get is going to be 0.075 times 4.5 square minus 3.5 square, and then plus 0.2 times the 4.5 minus 3.5. So that will give that probability. And for greater than 4.5, this last part, I'm going to put it over here. Greater than 4.5 would be integration from 4.5 to 5, because 5 is the upper bound. And then fx dx. Eventually, what we're going to get is 0.075 times 5 square minus 4.5 square, and then plus 0.2 times 5 minus 4.5. So that will give us the probabilities. So this example simply tests us the knowledge about the density function. First one is the parameter inside of that need to satisfy that the integration of the function on the entire possible range gives us 1. And then for the probabilities, we simply integrated the density function on the interval, give us probability. Next one, here is an example of a uniform distribution. This distribution happens a lot, particularly it is used to generate samples. In fact, all of the distributions are connected to uniform distribution in a way. So if you have any of the random variable, the random variable's probability of less equal to an x, if we change that x, make it to become a random variable, then this probability of any arbitrary variable less equal to a x, that becomes the uniform. But anyway, we don't have to be concerned about that. Let's just look at the definition of the uniform distribution. For a variable to be uniformly distributed on interval between A and B, then this variable, the PDF, is given by a constant on this interval. The constant, so basically, if you consider the interval A and B, inside of here has to be a constant. So in order to be constant, you know that this entire range will have a, when we integrate it, it's equal to 1. Therefore, the width is B minus A. Therefore, this height would be simply 1 over B minus A in order for the area to be 1. So that's the value. Constant is simply just 1 over B minus A when the x is between A and B. So that's the uniform distribution. Sometimes we also have a discrete uniform distribution. This one shown on the slide is the continuous uniform distribution. What is a discrete uniform distribution? Say x has a discrete uniform probability 1 over k for values x little 1. Let me call it A1 so you don't get confused with the random variable and also the value. A1, A2, A3. So these are the 3 values. And all of them have a equal probability.
Sorry, I'm
1
still
over
not sure
k.
about that.
Hey Siri, stop. So we assign probability 1 over k to each of these possible values, like A1, A2, A3, and up to AK. So there are k possible values and equal probability for all of them. Then this is a discrete uniform distribution. This next example, the direction of an imperfection with respect to a reference line connecting the valve stem on a tire to the center point is a random variable. The leg speed angle measured clockwise to the location of an imperfection. So this is talking about the tire valve. One possible distribution of x is uniform between 0 to 360 degrees. Give the PDF of x. So we do not really need to know too much about the background. So, but as long as we know that this x is uniform on 0 to 360, then we know the density function of x can be written as 1 over the upper bound 360 minus the lower bound 0. And that is if x is in this range, 360 and the 0. And for others, the density is simply just 0. This is the density function PDF. The next one, find the probability that the angle is between 90 and 180. Probability, we would always compute it with the integral here. So from 90 to 180, we put in the number and the dx here. So in this case, it's simply just this number times the 180 minus the 90. And that gives us 1 over 4. So going from 90 to 180, that's about a 90 degrees change. And this 90 degree compared to 360 degree, that's a quarter of it. So it makes sense that if the probabilities are evenly distributed, then the 90 degree compared to 360 degree is a quarter of the probability. What about the probability between 180 to 270? What's the probability of that? Is this one also equal to a quarter? So once you compute that, you will see that it is also a quarter. In fact, as you start from anywhere between 0 to 100 to 360 and end at a place where it's 90 degree above the starting point, then you always get the same probability. This is what the uniform is. Okay. The next example, suppose the reaction temperature in a certain chemical process has a uniform distribution where A equals -5, B is 5. Compute the probability of X less than 0. So for this one, it's uniform again, and we're given the A and B for X less than 0. So -5, that's a negative values that would allow us to have less than 0. So let's first write down the density function. It will be the 1 over b minus a. So 5 minus the -5. 1 over 10. So that's for x between 5 and -5. And for all other x values, we will have 0 for the f. Okay, so that's the density function, and then the probability of x less than 0 would be simply the integration from -5 to 0, and then we put in this x, sorry, not x, 1 over 10, and then the dx. The final result would be 0 minus 5, minus the -5 divided by 10. So eventually what we get is a half. So less than 0 is half. Imagine if you try to plot the density function, here is 0 and here's -5, there is +5. The density is a constant between -5 to +5. And then consider the negative part. This is about half of that, so that makes sense. It's half. Probability is half. The next one, -2.5 and +2.5. If you compute it, you'll find that integration will give us a probability of the 2.5 minus the lower bound and divided by 5, divided by the 10. The denominator, the 10 is because of the density function 1 over 10. And the numerator, upper bound minus lower bound, that's from the integration. So eventually, this one will give us also half. Similarly, for the next one, you will have the -2 and 3 are all inside of the -5 to +5. So this probability will be computed as 3 minus -2 and divide by the 10. And again, you will get half as the probability. The next line says that next part for k and k plus 4, all of them, both k and k plus 4 between -5 to +5, we want to compute the probability of x between k and k plus 4. This will be computed as the k plus 4 minus the k and then divided by the 10. And in this case, it would be simply just 4 over 10 as the probability. Okay, so in the uniform distribution, it does not matter where you start, and what it matters is that as long as the start and end points are both inside of the interval, then this probability only depends on how far is the distance between the start and the end. So like k plus 4 and k, the distance is 4. That 4 is determining the whole probability. It doesn't matter what is the k, as long as the k and k plus 4 is inside of the interval. For probability of 0, probability of any constant, for example, c, if we consider the probability, we integrate f on this same little point. because the lower bound, upper bound is the same C, therefore, when we try to do the integration, we can think of it as a C plus a very small thing on the upper bound and C minus a very tiny small thing, but this tiny thing need to be so small that it's close to zero. So when we integrate it, essentially, this is like, imagine you have the density curve here, and you have a C here, and when you try to integrate it, you are simply looking at an interval that's extremely small. And this integration is the area under the curve. So basically, essentially, what you're getting is the width here is the twice of this small in epsilon, and the height is equal to the density at that value, and then the area will be equal to the 2 epsilon times the height, and therefore this goes to zero as the epsilon is very small, close to zero. So essentially what we have is for any constant C, the probability of a continuous variable taking value being a constant, that's always zero. Therefore, a continuous variable probability of x less equal to C and probability of x less than C, that's the same, simply because this single value C does not really contribute to the probability. This is the case for a continuous variable. Is random variable x. Okay, but this is not the case if the x is a discrete variable. So, okay, maybe I should explain for discrete variable why it's not the case. So for a discrete variable, for example, x, for example, okay, x takes either value 0 or 1, and this 1 with probability of 0.5, 0 probability of 5. So with probability equals that. And in this case, we only have 2 possible values. And then if you consider probability of x less than 0.5, we'd better not put 0.5 because we want to consider the boundary. So we'll have this x less equal to less than 0. This has no possible value. So the probability is simply just 0. On the other hand, the probability of less equal to 0, that's in the case of x being 0. So for 0, we have half of the probability for that. Similarly, if you consider x less than 1, that's the same as 0.5 because the only possibility is x being 0 that has half of the chance. And x less equal to 1, the probability will become the 1 because we will have the x equals 0 plus the x equals 1. These two scenarios and add up together, probability is 1. So as you see, in the discrete variable, the less than versus less equal to, like this kind and this kind, they don't really have the same probability. Okay, so just be careful. If you work with a continuous variable, you don't have to worry about the single value. But if you are working with a discrete variable, you have to worry about whether that value is included in the probability calculation or not. The next concept we will learn is this CDF, cumulative distribution function. The probability of a random variable taking values up to a given x, the little x is a given value. So the little x here is x is a given value. For this given value, what's the probability of the random variable here? This one is the random variable r dot v dot for random variable. Random variable x less equal to this value. This is given by simply the integral from negative infinity to the little x from the density curve. This CDF function is used very frequently. So try to memorize the meaning of this term. So as you know that since the probability are given by the area under the curve, if we draw the density curve, then this is referring to all the area under the curve up to the little x. For example, like the F8, that means the probability of the variable takes value up to 8. That's shown on the left side of this picture. That's if we use density function on the plot, but if we use the CDF to plot it, what we are basically presenting is the CDF function when the x is 8, what is the value of that function? That's the CDF. Because as we increase the little x, we have more and more areas being included. Therefore, increasing x will only make the CDF getting bigger and bigger. Therefore, the CDF curve, if you plot it, it will always increase for a continuous variable. It will never decrease. Okay, so this one, this is always a non-decreasing function. I'm saying non-decreasing function because there will be some point that there are no probabilities assigned to those x. In that case, in that part, the CDF will be like a horizontal line. Okay, that's the CDF. CDF for many of the distributions, known distributions, if it's easy to compute, with that people compute. On the other hand, if it's not easy to compute, textbooks generally give some tables at the end of the book. Rather than using tables in this course, mostly I recommend to use the software such as in R. It's easily computed for this CDF. This example is about uniform distribution. And X be the thickness of certain metal sheet, and the thickness has a uniform distribution on AB. What's shown here is the PDF function, which is a constant, and also the probability of up to the little x. And so this part is simply just the CDF up to the little x. If we compute that, imagine if the x is less than a, then we don't have any shaded area to compute. Therefore, the probability is just 0. On the other hand, if x is bigger than b, then the shaded area would include the entire range from a to b. That would give us probability of 1. And if x is between a and b, when we compute the integral, what we get is upper bound would be the x, lower bound, even though we start with negative infinity, but the actual non-zero part would start from a. So the integration becomes 1 over b minus a, and integrate between a to x. When we finish the computing, we get this x minus the upper bound x minus lower bound a, and divide by this b minus a. So this gives us the CDF of uniform distribution. So once we have this, for example, if you want the f of half of a, half of a plus b, then what's the probability of that? You just put in this number, a plus b divided by 2 minus a, and here's the b minus a, and in the end, you'll find that this is half. So that's because this half of a plus b is just the midpoint between A and B. So that's this uniform distributions CDF. It's this one. It's good to memorize this one. You just use the upper bound X minus lower bound A divided by the B minus A. This upper bound X is the one that we want to compute the probability up to that X, but X has to be within A and B. So if we plot it, it's simply just the beginning part is 0 since we have no probability on that, and then we start to have this X minus A over B minus A. That's this the straight line with the slope. Slope is simply, this one has the slope of 1 over B minus A because this is what's multiplying the X. And then this part is a constant, that's because it's always 1. That's why it's constant. The CDF function can be used to compute probability, like between A and B. This probability will be computed with FB minus FA. And the probability of greater than A will use 1 minus the probability to the left of A. So it's 1 minus the FA. These are going to be used very frequently later on. So make sure you get comfortable with these. So that's the probability using the CDF. Again, in the continuous case, we did not have to worry about the boundary. So like when our computation is for A and B, including AB, versus including A but not including B, or just including B, not including A, or just not including A or B. All of these are going to give us the same probability of FB minus FA, but this is not going to be true if we have a discrete variable. For the discrete variable, for example, let's say if we have possible values are only integers. These integers, when we consider between A and B, including A and B, then A should be included inside of here. So when we try to do the subtraction, we need to subtract those below A. Therefore, this has to be A minus 1 when we subtract. For this one here, A and B, the A is not included. When A is not included, then when we do the subtract, this is fine to be FA. And this one, on the other hand, we have A included inside of this probability, but B is not. So since B is not included, we have to do F of B minus 1. And the other side, because A is included in here, when we subtract, remove, we have to remove up to A minus 1 rather than up to A. Similarly, the last one, since A is not in here, so we subtract FA. And the B not in there, we start with F of B minus 1. So that's the difference between a discrete variable versus a continuous variable. This is a discrete. We have to be careful if you work with discrete. There will be cases that the variables have discrete values. For example, you consider the number of successes after doing out of a fixed number of trials. And this, for example, if you have total number of trials being 10, and you for each of the trial, it will give you success or failure, and then the number of trials, total number of trials success being success out of the 10, that's a discrete variable. Similarly, let's say if you are trying to consider the number of hyacinth larvae that hatched becomes the adult hyacinth fly. You have a fixed number of, let's make it easier. Again, you have 10 of those larvae, and how many of them become adult? again, this is a discrete variable. Oh, this is talking about 10, that's still the same thing. Consider in the field on wheat, for example, peasant flies, they lay eggs onto the wheat, and then you try to consider how many of those are hatched. In this case, we may not have an upper bound, so the possible values are 0, 1, 2, 3, 4, all the way possibly infinity, because you don't really have an upper bound for the number of eggs laid by peasant fly. So in that case, this is also a discrete case. When we consider these probabilities, we have to be careful about the boundaries. This example, we have X is the dynamic load on a bridge. And here, the CDF is given. We want the probability that the load is between 1 and 1.5. For this computation, we just directly use 1 f at 1.5 minus f at 1. The reason that we can do that is this 1 and 1.5, both of them, the value were given in the CDF, so we can directly use the function to compute the probability for us. Okay, and for x greater than 1, greater is not directly inside of the CDF, so we use 1 minus less equal to 1. And for less equal to 1, that's simply the CDF evaluated at 1. And we can use put the 1 into the CDF, that will give us the CDF. Okay. The CDF and PDF are connected in the sense that since we integrated the PDF to obtain the CDF, therefore, if we take the derivative from CDF, we will get the PDF. So as long as the derivative exists for a PDF function, then the derivative will give us the PDF. Again, this is just for the continuous variable. If it's a discrete variable, we'll have to just take the difference, because the CDF in discrete is by summing up our possibilities. So if we have a discrete case, the PDF would be obtained by taking the difference between successive values of the CDF. Okay. Here's an example asking us to derive the PDF of uniform from the CDF. Let's say we have the CDF given by the X, so our CDF is given by this 0 and X minus A, B minus A, and the 1. This is if X is less than A, if X is between A and B, and if X is bigger or equal to B. So for this one, we can also put on the other side. Okay. So we have this CDF written that, and if we want the PDF, taking the derivative on this first part, this part, when X is less equal to A, we take derivative, will give us 0. Similarly, for X greater equal to B, we take derivative, we also get 0. And in the middle here, if we take derivative, we're going to get 1 over B minus A. That's why our density function is simply just 1 over B minus A. The next concept is the percentiles of a continuous distribution. Percentiles are defined as the value such that the probability to the left of that is equal to the given probability. Say P's percentile, 100 times P's percentile is this value that when you integrate from negative infinity to this value, that will give us the P as the probability. For example, 95th percentile would refer to the value such that the variable that's equal to that value has probability of 90.95. So on the, say if we plot the PDF curve, and then the percentile would simply refer to the value on the horizontal axis such that to the left is given by the P. And if we are using the CDF, this percentile would refer to the value on the horizontal axis such that the curve evaluated at this one is equal to that P. So this is the percentile. 90th percentile, for example, of X is 1.645. This means this basically means, okay, this is a statement, and this statement means probability of the X less equal to 1.645 is equal to 0.9. So that's the meaning of this percentile. For this example, we have the amount of gravels sold by a particular construction supply company in a given week. This is a random variable with PDF given here. Find the 50th percentile of the weekly sale. So basically, this 50th percentile is the value such that to the left of that is 50%. So we first find the CDF. This CDF, and then afterward we make it equal to 0.5, and then we solve for this value. So CDF here is from 0 to the X, and we put this function in there, density function. And when we finish the computing, we will get this function. And this function will make it equal to the 0.5 because the probability is 0.5. From there, we solve for the X. Okay. So here, if we try to make that equals 0.5, P is 0.5, solve for the X, we will get this percentile to be equal to the 0.347. This question is a little bit difficult for many of you because it involves solving an equation that has a cubic power, like it's to the power of 3. But just try to understand the concept. You may not really need to solve such equations in homework. The concept is that this is the one that we want to solve. This is the one we want to find. And here the P is given. So P's percentile, we have to find this X in there, and such that the probability is P. Okay. The next concept is the expected value. This is a concept that we use a lot. Expected value simply refer to the weighted average of the possible values. And what do we use for the weight? The X has a probability. Those all of those, each of the X value, we have the PDF function. So this PDF function essentially, if you imagine drawing in the, suppose this is the X here, and you draw a little very small interval that would be like around the around the X, and the height of that in the density curve would give us roughly the density function. So essentially, if you try to consider X multiply the f of X, you are basically using the PDF as the weight assigned to the X. And when we sum up all of those, because of X possible values are infinite between the interval, all of the possible values, therefore the sum up of all of the X with the weight of the density becomes the weighted. This is simply just the weighted average of all possible X values. All possible values. So that's the meaning of this expected value. As you see, it's considering all possible values, and we are taking the weighted average. So in order to get this mean, computationally, we can just directly compute this way, but the meaning of that would mean that if you're able to observe all of the possible values from this random variable, and you're going to take the weighted average, then you will have this mean. Because the calculation involves all possible values, so in real life, if you have not observed all possible values, you take the average of what you have already seen, only part of those values, then that what you compute is not going to be equal to this mean from the population. This population is using this mean is a population parameter. It is computed by considering all possible values of this distribution. Okay. That's for a single variable. And on the other hand, if we consider a function of this variable, say the h of x, and this function, the expected value would be computed as the function being weighted by the density of x, and then we consider all possibilities adding up. So this one is also a weighted average, but it's the weighted average of the function h on the with the PDF as the weight. So this is the meaning of this the calculation of the expected value. Here's an example. Two species are competing in a region for the control of a limited amount of resource. Let x be the proportion of resource controlled by species 1, and suppose x has uniform distribution on 0, 1. Then the species controls the majority of this resource would control the amount. Either say we have two species, species 1 and species 2. And if species 1 dominant, and that one will control more resource, then the h of x here becomes the value of x. On the other hand, if species 2 dominant, then the hx will be equal to the 1 minus x, because that's the proportion of resource controlled by species 2. So essentially, our hx is the maximum between the two, the x or the 1 minus x, depending on where is the x value. If x is between 0 to half, in that case 0 to half, then 1 minus x will be bigger because that value is going to be between the 1 and half and 1, so that will be bigger. On the other hand, if x is between half and 1, then the maximum between the two becomes x. So this is the function. And when we try to calculate the expected value of the amount controlled by the majority, then we would be calculating this function integrate. So when we calculate the expected value E of hx, what we're doing is really the h of x times the density. The density is just 1. Okay, so first let's write down the density. That's equal to 1 or 0 because it's uniform on 0 to 1. So this is if x is between 0 to 1. This notation, it means inside of 0 to 1. And this is the otherwise. The density is just 1. Therefore, we would just put the 0 to 1 here and h times 1 dx. That's the expected value. And since the hx takes different form on the different range of x, we'll split the two. One is from 0 to half, and in this case, hx is 1 minus x. And the other one is from half to 1, and this is the x. And then we simply finish the computation that will give us the expected value for h of x. Okay, so in this case, it gives us the final answer, just like 3/4. So the two species, if you consider the one that has the major control of the resource, that the one species that controls majority of the resource, what is the expected value? So what proportion of the resource is controlled by this majority species? And the answer is 3/4. A linear function, so this expected value has some special property if we have linear functions of variables. Say if you have ax plus b, this expected value, when we integrate, because a is a constant, b is also constant, when you integrate, this a and b can come outside of the integral. Therefore, expected value becomes a times the expected value plus b. So if h is a linear function, then the expected value of the linear function becomes a linear function of expected value. So that's something that's very good to have. Similarly, when we have two variables, for example, you have x1 and x2, you also have linear function a1 x1 plus a2 x2. And because of the linear, if we compute its expected value, again, it's the integration, but after we consider integration, this coefficient a1 and a2 can come outside of the expected value. So you will have the e of expected value of x1 and times the a1, and then plus the constant a2 times the expected value of x2. So this also says the same thing. Expected value of the linear functions becomes the linear functions of the expected value. So this is the expected value. And a1 times that plus a2 times the other. That's the linear function of the expected values. This is a very important property. Later on, we will use that pretty frequently. Okay. The next one here, the variance of a continuous variable that is defined as the squared deviation, average squared deviation, weighted average. Again, the weight is the probability density function. Squared deviation of what is the value deviated from the center, the mean. Squared deviation of that, we call this as the variance. Since we know that this is simply the expected value of x minus mu squared, and this computation actually could be simplified by, so if you try to consider this x squared, mu squared, and then minus twice of mu x, that's the extending the squared term. This expected value has three things linearly together, so we can have e of x squared. We have the mu squared and then minus 2 mu ex. Mu squared is a constant, it's not a random variable, so I do not need to write the expected value of mu squared. And the 2 mu is constant, so it comes out of the expected value. And here's x squared. Imagine when you have x squared in there, you integrate. You couldn't really put the square outside of the integral, so we have to keep the x squared inside of the expectation. And this one, the e of x is simply just equal to the mu. Therefore, it becomes like negative 2 mu squared. And then that cancels one of those mu squared. So in the end, what we get is this e of x squared minus the mu squared. Okay, so this part is just that. So now let me go back. So this part is done. The variance has the expected variance is the expected squared deviation from the x. It basically means that this is the average deviation, squared deviation from the center, from the mean. And if we take the square root of that, we call that standard deviation. This standard deviation is interpreted as basically the typical deviation of the value of the x from its mean, mu. But because it's the square root of that, we cannot really expect that the observed value would deviate from the mean by this amount. Instead, this is the typical deviation. You could easily see observed value to be 2 standard deviations away from the mean, or even like 3 standard deviations from the mean. That depends on the distribution. Okay. So for example, this is the PDF, and the mean is somewhere around here. This is the mean. and it's likely the standard deviation might be like above mu by this amount. So this one is the okay, this spot. Okay, that's the mu plus the standard deviation. And if you keep going, this one is another. This one would be the mu plus 2 standard deviations, and so on. And all of those from the lowest to highest are possible values. So the sigma alone is just like typical. We say typical because the majority, you see, there's the highest part that's inside of one standard deviation here. So that's the meaning of standard deviation. So if we have a linear function, we already know for linear function ax plus b, the expected value is simply the linear function of the mean. So a mu plus b. The variance here, when we consider variance, because of the squared term there, if we have a x plus b, if we consider the variance of that, it's going to be expected value of ax plus b minus the a mu and b. So the b and b will cancel. A, you will have a, square. You will have a square come out and e of x minus mu square. Therefore, this becomes the a square times the variance of the x. So for linear function of x, variance will have squared coefficient a squared times the variance of x. So this is something that we have to be careful. Every time when you consider the variance multiplied by some coefficient, then this variance will end up having squared coefficient times the variance of the variable. For example, let's say you have a measurement, and this measurement being subtracted. So instead of x, you are looking at negative x. What's the variance of negative x? Variance of negative x is equal to negative 1 squared times variance of x. Therefore, it's still equal to the sigma squared. Okay. So that's the variance. Here's an example, and for this is still talking about the weekly gravel sales. Expected value we have computed earlier, and now let's consider the variance. We first compute e of x squared, so we put x squared times the density, x squared, and then the density. So this part is density, and when we finish the integration, we'll get a e of x squared. And then we use the e of x squared here minus the mean square that give us the variance. Afterward, we take square root of that, it will give us standard deviation. So that's the calculation example. So variance and the standard deviation, they basically give us some sort of measure of how much data are have the variation compared to the mean. So that's all about this basic concepts regarding the distribution. So we learned the PDF, which give us a function such that under the curve between any two numbers, if we integrate that, it'll give us probability. We also learned the CDF. CDF represents the probability up to that value x, that's the CDF. If we want probability of greater than the value, we use 1 minus the CDF. And we also learned the expected value. Expected value simply means the weighted average of all possible values. The weight is the probability density function. And the variance is defined as the squared deviation, weighted square deviation from the mean. So all of the x values weighted square deviation compared to the mean. For linear functions of variables, the expected value of linear functions of variables becomes the linear functions of the expected values. And similarly, if we have linear functions of variable, the variance will still be linear function of variance, but the coefficient will be squared. So that's this part. Next lecture, next video, we are going to learn the normal distribution, that's a special distribution that will be used frequently.